Section 2.3, First-Order Linear Equations. So we're going to continue our foray into solving first-order equations in Chapter 2 with this next section where we look at, instead of separable equations, we look at first-order linear equations. So that means we have to be able to recognize when we are looking at a linear equation versus some other type of equation. So recall that the standard form for a first-order linear equation, it looks like a1 of x times y prime of x plus a0 of x times y of x equals f of x. So equation 1 is the template for a first-order linear equation. Now, since your coefficient function a1 of x can never be 0, otherwise this would not be a first-order equation, it wouldn't even be a differential equation, then since it's not 0, we can divide by a1 of x to get y prime of x plus a0 of x over a1 of x times y of x equals f of x over a1 of x. So that looks a little cumbersome. Remember, a1, a0, and f are all functions that we know. Y here is the only unknown. So if this is a known function and this is a known function, why don't we just rename this p of x? And if this is known and this is known, let's rename this as g of x. And now we'll call equation 2 the alternate standard form for a first-order linear equation. So any equation that is of the form 1 can always be put into the form 2 simply by dividing through by the leading coefficient. So this alternate standard form, our p of x is just a0 over a1, and our g is just f over a1. So our goal now is to solve equation 2. And so the idea here is, we're going to be a little creative, just following what people that came before us did, is we would love to multiply equation 2, multiply through by a function that we'll call m of x, m for multiply, so that the resulting form is readily solvable. Because if you just stare at equation 2, if p is known and g is known and y is not known, I really don't know what to do. I don't know what to do to try to solve this equation. It's not separable. I can't just separate the variables and integrate. I don't have that many tricks in my bag. So what do I do? So what we're going to try to do is multiply by this function m of x. We'll just take both sides and multiply by m of x. We'll distribute this through and we get this. And now what we want, or what we have, is this equals m of x times g of x. And then what we want is, we would love for this to consolidate or collapse down into m of x times y of x quantity prime. Now, just because I said that that's what I want to have happen doesn't mean that there's any m that'll make this happen. But bear with me for a moment. Suppose that there is an m that when I multiply both sides, I know I'm going to get this, and suppose that there is an m such that this line will collapse down into this line. Why would that be beneficial for us? Well, if that's the case, then I could work off of this line, and since this is a quantity prime, remember y is my unknown, m is my known multiplier function, then I'm really close to solving this equation, because if I can get rid of this prime, which I'll do by just anti-differentiating both sides, then this integral and this derivative undo each other, and I get m of x times y of x. And remember, this is my unknown. This is what I'm looking for. I'm trying to solve for y. And so we're tantalizingly close. This integral just is what it is. If m is known and g is known, then hopefully this is an integral that I can do. But at the end of the day, I can just divide both sides by m, and I get that y of x is 1 over m of x times the integral of m of x times g of x dx. So this solves for y of x. And this function m is called an integrating factor, and the reason it's called that, it's a factor because notice it's a factor. We've multiplied both sides. And it's an integrating factor because when we multiplied by this magical factor, it allows, assuming, I still owe you an explanation on this, assuming that this line collapses into this one, then it allows us to unlock y by simply integrating. So this is why it's called an integrating factor. So let me persuade you that I really can rewrite this form. I can find an m such that this yellow line will collapse into this yellow line. Okay? So how do we find such an m so that this process will work? Well, here we go. So we're just going to say that first yellow line equals the second yellow line. And now if you stare at this, I want this to be equal. I don't know that it's equal right now. I want this to be equal. But let's just calculate this derivative on the right-hand side using the product rule. If we do that, we get derivative of the first times the second plus the first times the derivative of the second. And so that means we want this to equal this. Well, if you stare at that for a moment, these are like terms. So if they are equal, then these will cancel each other out. And that means that this green underline must equal this green underline. Well, if these are going to be equal, stare at that for a moment. Remember, m is a function that we know, and p is a function that we know. Y is our unknown. So notice there's a common factor of y here. Assuming y isn't 0, we could just cancel the y. And when we do that, here I just took the same equation and I rewrote it without the of x's, m prime of x, y of x. I just wrote it as m times y prime, etc. So this is just a shorthand way to write this. But if you're looking at this line, the blues cancel, the greens must be equal, and since y is not 0, we can cancel the y's, and that gives us this. And if you stare at that, this is just dm dx, because this is the derivative with respect to x, equals m times p. If you stare at that, that is a separable differential equation in the unknown m of x. Remember, m is a function that we don't know. P is a function that we do know. So m here is the unknown. And this is a separable differential equation. So let's multiply both sides by dx and divide both sides by m. When we do that, we get dm over m equals p of x dx. If we anti-differentiate both sides, the integral here is the ln of the absolute value of m. The integral here is just, I don't know what p is. It's known, but it's known abstractly. In a concrete example, I would know p, but I can't really say what the antiderivative is right now. It's just the antiderivative of p of x, so we'll leave it like that. And we want to solve for m, so I'll hit both sides with a base e exponential. E to the ln of the absolute value of m is just the absolute value of m. And here we just have an e to the integral of p of x dx. If I drop these absolute values, I pick up a plus or minus sign here. And now I don't need to find every possible integrating factor. I just need to find an integrating factor that works. So I'll take the positive one. And we'll say m is the positive e to the integral of p of x dx. And this is the formula for an integrating factor. You really need to commit this to memory. It tells you that that is the recipe for the integrating factor. Okay, so if we go back to our equation, we can just say, okay, if we're confronted with an equation like this, I now know what the magic multiplier m of x is. The m of x function is e to the integral of whatever my p of x dx is. Okay, so now let's look at an example. So for a concrete example, suppose we have this equation. So remember, we have to put it in its standard form first, and really its alternate standard form. But first we'll get it in its regular standard form according to equation 1. And remember, that means we need to get everything that involves a y on the left-hand side, and if it does not involve a y, we put it on the right-hand side. So we need to export this to the left-hand side. When we do, we get this. And then to put it in the form of equation 2. So notice right now, my a1 function is 1 over x. My a0 function is negative 2 over x squared. And my f function is x cosine x. So this is a righteous first-order linear equation. But in order to use our integrating factor formula, we need it in the alternate standard form. We need it with the form that involves the p. So what we want to do is take this equation that's in its standard form. We want to rewrite it in its alternate standard form by dividing through by the leading coefficient. So remember, we had this. So we want to divide through by 1 over x, which is the same as multiplying through by x. We want to get a leading coefficient of 1. So if we multiply this by x, and this by x, then we get this. And now we can read off the p. The p is minus 2 over x, and the g is this function. But the key is we need to read the p off because that's involved in our integrating factor. So our integrating factor m of x is e to the integral of p of x dx. So that's e to the integral of minus 2 over x dx. You can just go off to the side and work this little integral if you want to. I just pull the minus out. The integral of 1 over x dx is the ln of the absolute value of x. Up here in the problem, they told us that x was positive. So since x is positive, I can drop the absolute values. When I do that, I just get an ln of x. And now I want to simplify this. And now remember that little property of logs from algebra. And that is a ln of b is the same as ln of b to the a. So that means this minus 2 can be moved. This is just algebra, not calculus. This minus 2 can be moved up into the exponent inside the ln. And the reason I want to do that is now I have an e to the ln of something. So these are inverse functions and they cancel. And I just get x to the minus 2. This is my integrating factor. This was the recipe for my integrating factor. But when all the calculus dust settled, this was my integrating factor. Okay, so don't lose sight of the prize here. We want to go back to our differential equation in its alternate standard form. We want to multiply both sides by the integrating factor. When we multiply both sides by the integrating factor, we know how this story ends. We said when we were developing this, if you go back to our yellow equations, if you multiply both sides by the integrating factor, then the left-hand side will always collapse to integrating factor times unknown function quantity prime. That's the way we cooked it up on the first page of the notes. On the right-hand side, it just is what it is. Now here these cancel, and I just get a cosine x. And now, keep your eye on the prize. We want to find y. So we need to get rid of this prime. We'll anti-differentiate both sides with respect to x. When we do that, we're doing the integral of a derivative, so we could just get the thing in the brackets. The right-hand side is a very straightforward antiderivative. We do need to pick up our constant of integration. Remember, this is a first-order equation, so you should get a one-parameter family of solutions, and that's exactly what we get. Right now it's in implicit form, but we can very easily get it in explicit form by multiplying through by x squared. And when we do that, in yellow, we get the explicit form of the one parameter family of solutions. So this is a general solution. And here, just to give you a feeling for what we found, remember c can be anything here. So if we just picked lots of different values of c and we graph these, this is the family of solutions that we're getting. And since we don't have an initial condition, we don't have c nailed down, and we get this one parameter family of solutions. Okay, let's try another one. Remember in the last section we looked at the very tame equation dy over dx equals x plus y. That equation was not separable. So if it's not separable, let's see if it's first order linear. So first we have to put it in standard form, so this needs to go to the other side. If we stare at this, it already has a leading coefficient of 1. It does match the template for a first order linear equation. So this is a first order linear equation. It's not separable, but it is a first order linear equation. I can read off that my p is minus 1, my g is x. The key thing is that my p is minus 1. So my integrating factor is e to the integral of my p of x dx. So that's e to the integral of minus 1 dx. So that's just e to the minus x. Notice I don't need a plus c when I do these integrals because I don't need to find the most general integrating factor. I need to find any integrating factor that works. And so by not worrying about the plus c here, I'm effectively taking the c to be 0. And so that will be an integrating factor that works. Okay, so now the process is I want to go back to my alternate standard form of the equation. I want to multiply both sides by my integrating factor. Don't overthink it. The left-hand side always collapses to integrating factor times unknown function quantity prime. The right-hand side just is what it is. So it's just x e to the minus x. And so now we're close to being done. We need to get rid of this prime. We do that by anti-differentiating both sides with respect to x. When we do that, the left-hand side is very straightforward. I just get the stuff in the brackets. The right-hand side, this is a classic example of I'm going to have to work for this just a little bit. Notice that this is an integral that you do with integration by parts. And so if you stare at this, I'm going to pick my u to be x, my dv to be e to the minus x dx, my du is dx, my v is minus e to the minus x. And you can go through and do this. This integral then is, remember the formula for parts, it's uv minus integral v du. And when the calculus dust settles, this is what you get for the antiderivative on this right-hand side. So why don't we just copy and paste this in right here and then add the plus c. Notice this is a non-negotiable plus c here. In order to get the general solution of this first order equation, we need to get that one parameter family of solutions. So we have to pick up the plus c here. Okay, so Notice here we had to use parts. In the last example, it was a really straightforward integral. It could be somewhere in between. You just have to do whatever you need to do in order to calculate that integral. And all the ones in the homework will be doable by your Cal 1 and your Cal 2 methods. Okay, so this is an implicit form for the one parameter family. We'd like to get it in explicit form, and we can do that by just multiplying both sides, everything on both sides by e to the x. When we do that, we get this. So notice the e, when we multiply by e to the x, here it cancels, here it cancels, here it cancels, and here we pick up an e to the x. So this is our one parameter family of solutions. It's the general solution for the original differential equation that we were studying. So this is why we couldn't do this in the last section. It was not a separable equation, but it turns out that it is a first order linear equation. It has a relatively straightforward integrating factor, but the integral on the right hand side took a little bit more work. And that's one way that these problems could get spiced up, is that the integral on the right hand side might take a little bit more work, and or the integrating factor when we're computing this might take a little bit of work. Again, geometrically, what we've got, if we want to visualize what this family of solutions looks like, just imagine that you pick lots of different values for c, and when you do that, you plot those resulting curves, and this is what you get, or at least a representative sample of what you get. So this is our one parameter family of solutions. It's very important for you to realize that when we have this, that we're not talking about a single function. We're actually talking about infinitely many functions, but they're all functions that have this one constant embedded in them. They're not infinitely many random functions. They're all fruit from the same tree, and the only way that they differ is by this constant. Okay, so what about initial conditions or initial value problems? So in the homework, you could be given a first order linear equation where it's just a differential equation, or you could be given a first order linear equation where there's also an initial condition. And so you're solving an initial value problem. But just remember the motif from last time. If you're going to solve an initial value problem, what you're always going to do is just find the general solution to the differential equation, and then apply the initial condition to nail down the c, and then plug that value of c back into the general solution to get the particular solution. So for this one, since I'm recycling this differential equation, we just did this, we already found the general solution. So here it is. So now we just need to apply the initial condition to determine the c. So I'm looking at this. I'm going to let x be 1 and set y to be 2. And when I do that, I get this. That's an algebra equation in the unknown c. When I simplify this and solve for c, I get c is 4e to the minus 1. Now this is not my answer. I need to return back to the general solution and plug this value of c in. And now the solution to the initial value problem, try to get these on the screen all at the same time, it's just this with this value of c. So this would be totally fine with me and or my lab. Or you could simplify this. This is unnecessary, but for cosmetic reasons you might want to do this. Notice you can combine these terms like this. These are both completely acceptable. And this would be a particular solution. It's one member from the family, and it's the one member that has this value of c. Or I think a better way to think about it, it's the one member that passes through the point 1, 2. So to go back to our family of pictures, there's a whole bunch of solutions to this. But if you wanted to pick out the one curve that passes through the point 1, 2, then this is your curve that you want. Okay? So in the homework, you're going to see some examples where there's just differential equations. You're going to see examples where there's differential equations together with an initial condition. The second is you just do a little bit more than the first. You just go ahead and find the general solution using the integrating factor technique, and you will have to refresh yourself on maybe some techniques of integration, or just they're not going to be too fancy. You can usually do these with a little algebra or a little u substitution or maybe an integration by parts. It's not going to be anything overly fancy. And then you compute the solution to the differential equation. And if you have an initial condition, then you just do what we did in these last examples to nail down the c and replace that back into the general solution to get the particular solution.